So, welcome everybody to this live chat for with the Kavli Foundation. I'm Chris Martin, the Director of Physical Sciences for the Foundation, and I'm joined today by Dr. Addie Foord. Addie is the Porat Postdoctoral Fellow at the Kavli Institute for Particle Astrophysics and Cosmology at Stanford University, and she uses X-rays to learn about black holes. So Addie, what first got you interested in black holes?
So I think it was probably in undergrad when I took one of my first astronomy courses, and I learned that we know about, a million or more of these sources of supermassive black holes, at least. And there's still like so many questions surrounding their origin and their growth and their evolution. And then one of my first research experiences in undergrad was actually studying a certain subset of supermassive black holes called blazars, which are these really extreme systems which have jets, and their jets are pointing along our line of sight, and we can study them across a range of wavelengths. And I think that first research experience is what got me like very, very excited about supermassive black hole research.
That's really cool. So I did over a million black holes, and we've known about them for so long. And from how do we know about all those million?
So there's a lot of different detection techniques for supermassive black holes. The really great thing about supermassive black holes is that they emit, all the way from radio wavelengths up to X-rays. And so with all of the wonderful telescopes that we have, we can go about detecting them in a variety of different manners. And, some black holes might emit in radio, others might not. And so, because we kind of have like a really good coverage of the multi wavelength sky, we've been able to detect a really large amount of these systems.
So if there's so many of them, do you have one in particular that's your favorite?
Yes, I do. And this might not be the most exciting answer, but it's the real answer. My favorite black hole is definitely Sagittarius A star, which is the black hole in the center of our Milky Way. It's a pretty I would call it a chill supermassive black hole. It's not really doing much. It's not eating a lot of material. It's not very active, and if we were actually outside, it's actually representative of most of the supermassive black holes in our universe. Most of them are relatively quiet and they aren't super active. So I think it's really special that we have the opportunity to observe one of these quiescent supermassive black holes only because of our proximity to it. And because of that, it's just one of my favorites.
Sagittarius Star is one of my favorites as well. Turns out I looked at Sagittarius A, the stuff that was around it. And obviously, Sagittarius Star has been in the news lately with the Event Horizon Telescope actually seeing the shadow of its event horizon. I guess that's sort of in the radio. And the Nobel Prize just a couple years ago was also about infrared stars going around it, seeing it was there. But you're able to see it in X-rays as well. How does that happen?
Yeah, so as observers, we are able to not actually see the supermassive black hole, but see material around it, right? A black hole is black in that not even light can escape its gravitational force. So the accretion disks that are around these more active supermassive black holes um, emit, all the way from optical wavelengths through UV and X-ray. And as you get closer and closer to the center of the supermassive black hole, the accretion disk gets hotter and it will emit in higher energies. So the X-ray wavelengths are sensitive to accreting supermassive black holes, and we're looking at emission that's like very, very close to where the radius of the supermassive black hole sits.
So I saw a question pop up there. What makes a black hole active? Let me flip that, I guess, to Sagittarius Star. Will Sagittarius Star be active at some point, and how will it become so?
Yeah, so that's a really good question. And to take a step back, we think that Sagittarius Star might have been active in the past. For example, because we see evidence of things like the Fermi bubbles, we see evidence of kind of like gas that has been pushed out from the center of the Milky Way, and it looks kind of like plumes of maybe residual jets, for example. And it's likely that Sagittarius Star could become active again in the future. The question of what makes a black hole very active is one that we are still trying to understand as a community of researchers. We think, for example, that mergers can induce activity into supermassive black holes. Anytime you give the supermassive black hole the opportunity to swallow lots of gas and dust, it will do so, and it will likely become active.
And so mergers is right along the lines of what you do. You're looking for pairs. How do you find those pairs and how do you see if they're going to merge?
Yeah. So merging supermassive black holes. So they're not easy to find. And as I noted earlier, we're only sensitive to finding supermassive black holes when they're actively accreting. So you could have two galaxies that are in the process of merging, and each one of them have their own central supermassive black hole, but you might not be sensitive to actually detecting the black holes that are there if they're relatively quiescent. So I'm searching for actively accreting pairs of black holes, and I'm using X-ray data to do so. And the X-rays are special because, as I noted earlier, they're sensitive to kind of the closest region right around the black hole. And so we're sensitive to like the smallest scales of black hole accretion. And so what I'm doing is kind of going through the thousands of available X-ray observations of supermassive black holes that have already been taken, and trying to figure out if any of those observations show evidence of two accreting things being there, basically.
So how many of these have you found? You said there's thousands of observations. How many pairs have you found?
So I think my number right now is close to like 15 or so, which sounds small, but I will note that at least in X-ray wavelengths, we know less than maybe 60 of these sources. So it's a pretty big fraction of the known X-ray population of pairs of black holes. And one of the best ways to really increase that number is to look through all of the archival data that's available. And so luckily, with telescopes like the Chandra X-ray Observatory, all of their archival data is public, and it's available for people like me to analyze.
So maybe this is a good point to see what an X-ray pair would look like. I think we've got a little video of that. Maybe you want to narrate what we'll see?
Yeah. So this is a timely video given what was just released by the Event Horizon Telescope. This is a simulation of what the shadow of a binary pair of supermassive black holes would look like. So if we could point the Event Horizon Telescope toward a pair of merging supermassive black holes, and if we were able to resolve both of their event horizons, we would see emission as shown in this simulation. So, we currently don't have the capabilities to do this, but maybe in the future, when we can start making videos or, time resolution with event horizon observations, and we stumble upon a binary pair, we can see something like this.
And so how fast, I guess depends on how close these black holes are to each other, how fast they go around like this.
Yeah, so the actual act of merging can take hundreds of millions of years. And as you're right, as they get closer to one another, the orbits will increase, and their distance will decrease in an increasing amount of time. And so for the scales that the event horizon is sensitive to, when you can start resolving the shadows of each of the supermassive black holes, these two systems are on the verge of merging, so they're at probably the smallest separation possible before merging into one black hole.
So given how long it takes, are any of those 15 pairs that you found gonna merge anytime soon?
No, definitely not in my lifetime. No, it will be millions of years. We're really limited currently by the resolution of our telescopes in finding two things that are emitting light and are next to each other. For the video that you just saw, a pair that is that close to one another, you could not resolve with most telescopes besides the Event Horizon Telescope. So for the pairs that are on the verge of merging, we really aren't going to be sensitive to finding them with our current telescopes.
Yeah. So maybe it'd be useful to see what images from actual telescopes look like. I think we've got, yeah.
Yeah. So as I said, supermassive black holes emit over a wide variety of wavelengths, but the wavelength that you're looking at and the resolution of that telescope is going to give you drastically different information. So this is a pair of supermassive black holes that we were able to find using the X-ray data. And if you look at the infrared data, it just looks like a single blob. You wouldn't even know that there were multiple galaxies there. And this is just because of the resolution of that infrared telescope. This system then got follow-up observations in optical using the Hubble Space Telescope, which is a higher resolution. And we were able to resolve 3 galaxies there. So it was a merger between 3 galaxies. Then the question of, well, do each of these galaxies have an accreting supermassive black hole? That we turned to X-rays, or we're able to resolve the emission right at the center where a black hole would be. And when we looked at the X-rays, we only found evidence for 2 accreting supermassive black holes. So only 2 of the galaxies had active supermassive black holes. So the mismatch between what optical data shows you and what X-ray data shows you can give you more insight kind of on the environments of black holes. What does it tell us if there are 3 galaxies there, but only 2 have strong X-ray evidence for black holes? Is that telling us it's a dusty environment, et cetera? And so connecting X-ray results to optical results and infrared results are really important to better understanding the environments of these supermassive black holes.
So I gather, the environments around them is actually really important, for what you're looking at. How, what sort of environments are important? What would you find really interesting for an environment for a black hole?
Yeah, so from what we've been able to find so far, we're learning that in merging systems, black holes tend to like gaseous and dusty environments. So the mergers that had the highest levels of gas and the highest levels of dust had more active supermassive black holes in them than the ones that had lower levels. This isn't entirely surprising because we know that supermassive black holes like to eat gas and dust. But in order to really quantify other parameters of the galaxy that might be important, like the mass of the galaxy, for example, or the star formation rate of the galaxy, and how maybe that affects the supermassive black hole activity as well, we're going to need much larger samples of supermassive black hole pairs. And so I'm trying to continue doing all of these multi-wavelength studies, but on a much larger scale. And so hopefully by analyzing these thousands of X-ray data sets, we can start getting a much larger sample and really better fine-tuning what we know about the importance of the environments for supermassive black hole pairs.
Well, I guess another interesting part about that environment is it's the galaxies themselves of how they're connected to the black holes. I mean, so that previous image you had, those galaxies. So how do galaxies and black holes interact with each other? How are they connected?
Yeah, so that's a really good question, and it's something once again scientists are trying to figure out. So the radius of influence of a supermassive black hole is very, very small with respect to the radius of a whole galaxy. So size-wise, it's similar to a marble sitting in the center of our sun, right? So the galaxy doesn't really know that the black hole is there. Its gravitational radius of influence is really, really small with respect to the size of the galaxy. But we see that the mass of the supermassive black hole tends to be linked with properties of the galaxies, like the mass of the galaxies and the velocity of the stars in the galaxies. And so we think that something must happen where the galaxy does learn about the supermassive black hole in the center. And so one of the most popular theories is something called feedback, where basically the supermassive black hole is able to have a larger scale influence on the galaxy through things like jets. Or through things like winds that we think might come off of the accretion disk. And this allows the supermassive black hole to just have a larger radius of influence that might affect the certain properties of the galaxy as it's evolving through time.
No, this has been really cool. I'd sort of, I guess, as a final question, if we came back to you in 10 years or 20 years, what do you think would be the coolest thing that you're hoping to figure out?
Oh man, that's a really tough question. So I think for the supermassive black hole community as a whole, one thing that I really hope we figure out is the origin of supermassive black holes. So how do these things form? That is still one of the biggest unknowns when it comes to supermassive black hole theory. We don't really know how they could have formed. And so, hopefully, with future telescopes such as JWST, possibly future X-ray telescopes that might go to space that will be sensitive to some of the earliest supermassive black holes in our universe, we'll start to learn a little bit more about formation mechanisms for them.
No, this is really cool. So thank you so much. This has been Adi Foord, the Porat Postdoctoral Fellow at KIPAC, the Kavli Institute for Particle Astrophysics and Cosmology. So thank you.
Thank you so much.